Hello, everyone. I will now present our paper Gradient-Based Sampling for Class Imbalanced Semi-supervised Object Detection. In recent years, there has been impressive success in semi-supervised object detection. However, the benchmark datasets are assumed to be class-balanced or slightly class-imbalanced. This underlying assumption can be easily violated in real-world scenarios. For example, the sample distribution of corner cases in autonomous driving is scarce. So the performance of previous SSOD methods often suffers in extremely class-imbalanced datasets. As you can see, the recall of pseudo-labels of minority classes is much lower than that of majority classes. We observe there are two types of confirmation bias when applying the previous method. The first is the confirmation bias toward majority classes. In this figure, the recall of minority classes is much lower, so there are not enough pseudo-labels for minority classes. The second is the pseudo-labels of minority classes are prone to be incorrect. As you can see, the precision of minority classes is much lower than majority classes. It means most of the pseudo-labels are incorrect and disturb the learning of detectors. To comprehensively study the class-imbalanced problem, we propose a new setting, namely class-imbalanced SSOD. We consider two scenarios with different distributions in unlabeled data. First, there are abundant unlabeled instances for the minority classes in the unlabeled images. This means the implicit instances for minority classes in unlabeled dataset are enough. Second, the instances of minority classes in unlabeled images are naturally scarce. To tackle two types of confirmation bias, we propose a simple yet effective gradient-based sampling framework for CISSOD. It consists of three modules. The GBR module dynamically optimizes a set of gradient-based linear equations to obtain the class-wise balancing weights. The GBT module, guided by the class-wise balancing weights, then performs adaptive thresholding to obtain class-balanced pseudo-labels. The CRS module performs image-level data resampling onto with respect to the confidence and thresholds from GBT. Our method is agnostic to all SSOD methods. For a given class, the gradients of all samples that possess the specific class label are referred to as positive gradients, while the gradients of samples from other classes are referred to as negative gradients. They can be estimated from the derivative of the classification loss function to class logits. For each foreground class, we expect the positive gradients and negative gradients to be equal. To achieve it, we can generate n equations regarding the class weights as equation 3. Besides, in order to keep the scale of weights unchanged, equation 4 is added. Because traditional linear equation solutions always fail to solve the weights, we introduce a Jacobi iterative module to solve the equations. The weight is updated by Jacobi iterative with an auxiliary loss to align the learnable logits and the target logits. We also design a gradient-based thresholding module. The aforementioned class-wise balancing weights are utilized to generate thresholds for each class. The class rebalancing sampling module resamples the unlabeled images. The sampling rate is based on scores of pseudo-labels and the thresholds in GBT. As mentioned, we introduce two scenarios with different distributions in unlabeled data for CISSOD. We set up three subtasks to validate our method. We visualize the precision and recall of pseudo-labels with baseline, EQLv2, and our method. Obviously, the pseudo-labels in our method are more accurate, alleviating the second type of confirmation bias. Our method also mines more pseudo-labels for minority classes, alleviating the first type of confirmation bias. We also show the norm of positive and negative gradients and class logits with and without GBR. It shows our GBR achieves more balanced gradients and more balanced class logits.